And I mean, welcome everyone. Welcome to today's seminar. We are excited to have with us Dr. Andres Valencia from the University of Canterbury, New Zealand. Today, Dr. Valencia will share his experience and the expertise in dynamic of wildfire through the high-resolution remote sensors. So let's give a warm welcome to Dr. Valencia. Like, the virtual stage is yours.
Thank you. Thank you very much. So Josh is gonna talk. Sorry. Cyril, do you want me to start now or?
Yeah. I mean, we recording it and we going to upload to our SFP YouTube channel as well.
Okay.
So yeah.
All right. So first of all, thank you very much, all of you, and also the people watching this in YouTube. So first of all, thank you the SFP student chapter from UQ for the invitation for this to provide this seminar. I'm very happy to do this. So as Zero you mentioned, I'm gonna talk about wildland fires and remote sensing. So I'm gonna just show you the plan of this presentation. First of all, what we have is a quick introduction, just contextualizing the seminar, which is basically talking about wildland fires. Then I'm gonna talk about two projects that we have carry out. It's actually ongoing projects involving remote sensing and also intensity or heat release rate. It's basically energy produced by the fire. So the big, let's say the core of this seminar is how to use remote sensing to estimate the amount of energy released by the fire. So in introduction, I'm going to talk a little bit more about intensity and heat release rate, what it means, what is important. And then I'm going to show you two examples in which we use remote sensing to do this. One for shrub fires and the other one for grass fires. All right. And finally, I'm gonna also talk about some future works and acknowledgement, and answer some questions. At the end, you can follow the presentation with this bar located just at the bottom of each slide. All right. Do you see well my presentation? All good? I continue?
Yeah, all good. Yeah.
All right. Excellent. All right, so I'm going to start with the introduction and just, what is the context of this research. So, as you know, communities around the world are being exposed to more fires more frequently and also with higher severity, like more destructive power. This is something that is happening in some fire-prone countries such as Australia, or for example, the US and California, for example, or also some countries in the Mediterranean sea, for example, Greece, Portugal is another example. But it's also happening in some countries like New Zealand or Colombia, for example, countries that historically have not been considered like fire prone, right? So is a phenomenon that is happening in countries like New Zealand. This is one example. The Lake Ohio fire that took place in the year 2020 is the most destructive fire that we ever experienced here. We're also seeing the fires approaching the city, so those wild and urban interface fires. So is a kind of a shift of regime. We have fires that chose a more destructive behavior and destructing more communities, houses, infrastructure, and also impacting more people. So this is one example of what I'm saying. This is a photo from Google Earth from Maui in Hawaii just before the fire. And this is after the fire that took place in the year 2020. You can see that basically all of the buildings, they were, oh, something happened.
Yeah, like your screen stopped to share.
Ah, interesting. All right, this meeting is okay. I'm gonna restart.
Yeah, no worries.
So it's maybe not the right one. I'm gonna stop sharing and restart again.
Yeah.
So let me just see this. All right. Now if I share my screen, I think I can just show. Do you see it now?
Yeah, looks perfect.
All right. Let me just come back where I was. Do you also see the mouse or not?
Yes, we do.
Okay. Okay. So I was here showing you before and after the fire that took place in Hawaii. So this is just one neighborhood, but you can see the level of destruction that, you know, this wildfire specifically produced in this place. And the problem is that when the fires move from a purely vegetation fire to a house and vegetation fire, then you have another dynamics that involves also, you know, classical fire engineering, you know, science, flashover, and all these kind of things. So you know, we're experiencing, we're seeing these type of fires destroying more communities. Another example is Valparaiso fire this year, which we saw a similar level of destruction, right? And on the top of this, there are more reports about dynamic behavior. Like one example of dynamic fire behavior is, for example, extreme fires or some type of non-linear, non-steady behaviors. Quick accelerations of the fire, for example, is another example of dynamic fire behavior, right? Like unpredictable behavior from wildland fires that can actually make them more difficult to predict and study, right? What is happening now is that the current methods to measure, quantify, and predict wildfires, accounting for this, what I'm saying, dynamic fire behavior, and also wild and urban interface fires, fall short to capture this type of behavior, right? So in this context, in the context of improving our understanding of this type of behaviors, but also to improve our capacity to predict this type of fires, remote sensing is actually a very, very useful tool. I just named two here, satellites and drones. But you know, there is all other type of remote sensing tools that can be used for the study of wildland fires. Satellites are actually an amazing tool. The reason is it allows for capturing spatial and temporal behavior of the fire for very large scales, right? So you can have, for example, you can see the development of large fires throughout days. You can also with satellites you can also look at fires that happened maybe 10 or 20 years ago and find those patterns that allows us to know if fires are actually increasing or decreasing over time. Satellites also, depending on the of the tool that you use, but for example, hyperspectral cameras allows us to understand the type of vegetation that we are dealing with, and to couple those characteristics, what we call the spectral signature of the vegetation, with the flammability attributes that we can measure in the lab. This is an ongoing research we are doing here at the University of Canterbury in collaboration with some colleagues at the Australian National University. But it's not the topic of this research. It's just to highlight how useful satellites are, right? We want to focus on drones, UAV technology. Oh, stop again. I'm not doing anything.
Yeah, it seems like, but I mean, take your time.
Yeah, it's weird. So I'm gonna restart, but I'm not touching anything. This is weird. Okay, I'm gonna try again, okay?
Yeah, no worries.
Okay, we are here. We're talking about drones, and I'm gonna share, maybe what I'm gonna do is I'm gonna share I don't know why it's stopping to. What about
Yeah,
this?
now it works. Now it works.
It works?
Yeah.
All right, I'm gonna continue. So I was saying that, you know, we have satellites. So there is an amazing piece of equipment, provides a lot of different options to study fires and at the largest scale. But then what is interesting from drones is that they provide a higher spatiotemporal resolution. It means that we can measure things. We can measure the fire at the fine scale. And when I say fine scale, I'm talking about sub-meter scale. We can also measure the fire, the behavior of the fire at the small, over, let's say, fine temporal scale. So in this case, sub-second, right? Allows us to capture things as, for example, turbulence or interaction with the atmosphere, right? Or mechanisms of a spread, right? So allows us to have access to some specific metrics and aspects of the fire that that still fine, and allows us to improve our understanding and develop new models to actually quantify the behavior of the fire and predict it. Some example of a drone technology. So the sensors that can be used attached to drones to study wildfires is infrared cameras, RGB or visual kind of cameras, spectral devices, like for example hyperspectral cameras too, or LiDAR, which provides a good estimation of the structure of the vegetation, right? So we're going to be talking about some applications of UAV technology in the analysis of the behavior of wildland fires. And I want to be specific about what I mean by wildfire behavior in the context of this presentation. And to do so, I'm just going to spend maybe a couple of minutes talking about wildfire behavior and the way I see this, and why energy, why heat release rate or intensity or power of the fire is key to understand the overall behavior of the fire. So if we look at fire or wildland fires from what I call a thermochemical scale, basically molecular scale, we have a very simple framework to explain combustion, which is the fire triangle. We have oxygen from the air, fuel that is produced from the vegetation once they pyrolyze, and then some kind of pilot or heat that produces the fire, right? Once the fire is sustained, the fire will produce energy. I'm using big Q dot, which basically means energy produced, energy released by the fire, right? So this combination of factors provide a way for the fire to release the energy, and this energy release is what makes the fire dangerous, or what make the fire is basically, it can be related to the ability of the fire to harm, the potential of harm of the fire, right? If we look at the wildfire behavior from the landscape scale, so let's say several meters, usually the main it is described in this way. The main three characteristics of let's say the main thing, the main external factors affecting the way in which the fire behaves are often listed as weather, topography, and vegetation. And then those three things, they create what we refer to as a wildfire triangle, which basically account for the different, the relative contribution of each one of those three factors in the way in which the fire behave. And again, when I say the way in which the fire behave, I'm talking about, for example, the power of the fire, or the speed of propagation of the fire, or the acceleration of the fire, etc., etc. Now, those two triangles that I'm talking about here, they, let's say, interact somehow, and they define what we can refer to as the exposure mechanism: radiation, convection, and burning embers. It's basically the way in which the fire release the energy, transfer the energy, either for propagation purposes, either because you want to transfer the energy to heat up the unburned fuel in front and then keep the fire going, or also exposure in terms of harm. So for example, the ability of the fire to ignite a building or to hurt somebody comes from here. Now, all this, what I'm saying is just to come back to this idea of energy. At the end of the day, the energy released by the fire, for whatever condition we're talking about, is what will drive the ability of the fire to produce those exposure mechanisms, to produce this ability to spread or to move or to hurt, right? At the base, the production of energy, the rate at which the energy is produced, is what is making the fire produce, for example, more embers or produce more radiation or more convection. So quantifying this energy release rate or this intensity or this production of energy is key for us to characterize and identify the mechanisms in which the wildfires can be dangerous, right? So there are two main ways in which we can define this energy, this potential of harm, this ability, this power of the fire. The first one, which is kind of the classical fire engineering way, which is heat release rate, very, very important variable that accounts for the total amount of energy that is produced during the reaction, often measured, for example, using calorimetry. And in the context of wildland fire, it can be defined as the power of the whole fire, including the front of the fire and also the back of the fire. Basically, the power or the rate of production of energy that comes from the whole burning vegetation, if you want. Now, in wildland fire, we often talk about intensities. Is a very useful and very useful and insightful actually metric, which accounts for the power or the energy produced by the moving fire front. Accounts for two things. The first one, the fact that the fire front is the part of the fire that is moving quickly. And the second one, it accounts for the fact that the fire front is moving, right? So both of them, they have kilowatt. It means that we're talking about production of energy, but they have different use. So I'm going to name just three of them. The first one is that both heat release rate and intensity, they are associated to the size of the fire. So literally, how big is the fire? And the ability of the fire to spread. Why? Because the more energy you produce, the more energy you're able to transfer to other unburned fuel, and just to keep the whole spread of the fire going. The second one is that actually intensity in this case is one of the metrics used in construction standards and guidelines to build buildings in the wild and urban interface in some standards, right? So it's explicitly used to calculate, to define, what type of provisions should the engineer keep in mind to build buildings in areas that are fire prone. And finally, in this case, intensity is used in risk mitigation and emergency activities all around the world. Actually, this intensity metric is used, for example, to see how difficult it is to suppress a fire. For a certain intensity, how likely or what type of requirements, what type of equipment are needed to actually suppress this fire, right? So it's a good metric to estimate the size of the fire, but also the resources that should be used in order to suppress it, right? So it's very, very useful for emergency for firefighting protocols, for examples, right? I would like to highlight something, and is this idea of intensity and heat release rate used in construction and standards, right? So one way in which intensity is used in this type of for this type of activities is to estimate, for example, the height of the flame, and from the height of the flame, then engineers can actually estimate also the radiant heat flux. And from the radiant heat flux, then we're able to define some areas, and for each area, some provisions, some requirements to build, right? The problem is that although intensity and heat release rate are extremely important for this type of design purposes, today the calculations are often limited by, estimating a single number or using a very, let's say, simple calculation that allows to get just one average values of intensity that sometimes result in under estimation, or let's say under or over design, right? So there is not a good understanding of how to, let's say, use the intensity, what values to use, or what are the uncertainties associated to it in order to calculate exposure from it, right? So in few words, what is needed today is new methods capable of quantifying and characterizing energy production from wildland fires, and remote sensing actually helps, is a good tool to improve in this area, increasing our understanding of interaction between the fire, the fuel, and also the atmosphere. This is in the context of fire dynamics, dynamics fire behavior, and then also improving current models to estimate wildland fire impact. So what I'm going to do now after this introduction is to talk about two projects. All right, the first one deals with prescribed shrub fires and intensity, and the second one with grass fires and heat release rate. All right, and also this is a good opportunity for me to showcase some of the research activities that we are doing here at the university and some of our colleagues, and show some of the cool things that we are actually carrying out here. So let's talk about the first one, and I name it shrub fires, but it's basically a method to estimate intensity from shrub fires using remote sensing, right? So this is one experiment that was done as part of a big project led by Scion, which is a forestry institute here in New Zealand, in collaboration with the U.S. Forest Service, San Diego University, and other colleagues in the university, for example, Marwan Katurhi and his team. And what we basically have done here is, it was a lot of experiment, but this specific experiment was was a plot of 150 meters by 200 meters. So this is what you see here, and this is a camera that was inside the plot. So what you see here is that the plot was actually dominated by gores. The canopy height was more or less 1 meter, but can go up to 2 meters. The temperature was 23 degrees Celsius, pretty dry conditions. And then what we've done is basically, ignite the plot with a line here. We kept it as a line until half of the plot, and then we allowed the fire to take its natural parabolic shape. So I'm going to show you that a little bit more. Sorry, I'm using my screen, but maybe you don't see the mouse. So, we ignited here as a line.
Well, actually, it's okay. We can see it as well.
Oh, you see it? So you see it
no
here?
Worries. Yeah.
Oh, interesting. Perfect. Okay. So this is hopefully give you an idea of the type of experiment that we've done. So the instrumentation that we use included two drones, one before the fire and one after, during the fire, sorry. So before the fire, we had one drone with one sensor attached, was a LiDAR. LiDAR is basically laser scanning that allows for basically getting a map of the height of the canopy or the structure of the canopy. And then during the experiment, we used another drone with an infrared camera. And the idea was to actually look at the dynamics of the fire. In this case, track the fire front over time, right? So let's have a closer look to both of them. So from LiDAR, what we got is basically, after post-processing of the raw data, which is basically a cloud of points, or let's say a 3D map of the canopy, we can get this map, which is basically the height of the canopy at a very high resolution. I don't remember exactly how was it. I think it was something close to 30 centimeters by 30 centimeters, but it was very, very fine. And basically this map allows us to get a pretty good idea of the structure or the morphology, if you want, of the plot. I would like just to point out that the fire was ignited at x equal to 0 and moved until x equal to 200, right? So horizontally. Then what we've done is that we took this map and then we use a model that was developed by one of our collaborators, Grant Pierce, some empirical model that was developed from a lot of different measurements, like sampling of gores in New Zealand. And then it allows us to get an estimation of the fuel load. Fuel load means how many kilograms of gores we had per meter square, basically. And then we multiplied this by the fuel consumption. It was close to 0.72. Sorry, 72% or 0.72, which we estimated from destructive sampling, means before the experiment, measuring how much fuel there was, and after the experiment, measuring how much left, right? So 72% in average was the amount of fuel or vegetation that was consumed during the fire, all right? So we get this beautiful map of consumed fuel load or consumed vegetation in kilograms per meter square. So this is what we did from this side. Now, from the other side, during the experiment, we took a video, infrared video of the propagation of the fire. This is one single frame of this video. That's more or less how it looks like. So what we've done is basically we apply an algorithm or a model that, no, it was more like an algorithm that was developed here at the University of Canterbury and published in the year 2022, which basically allows us to get a pretty good indication of the location of the fire front over time, which is what you see here. So this is the fire front at 1 minute, 2 minutes, 3 minutes, right? And it was moving this way. You can see that when it reached 100 meters, then we allow the fire to get this parabolic shape, basically developing a single fire front and the flanks of the fire. And then we apply another method that is also published to calculate to map the speed of propagation of the fire front, how quickly the fire front was moving everywhere, right? And this is what we get, just basically a map of what we call the rate of spread or speed of propagation of the fire front. Then with those two maps, what we've done is that we multiply both of them, and then we also multiply by the heat of combustion, which was measured in our lab. And then we were able to get this beautiful map of intensity or production of energy from the fire front, if you want, right? And that's what I want. That's our main result. That's what I want to share with you. I'm going to give you some information about this. So the first thing is, when you look at this map, basically this map is telling how much energy was produced by the passage of the fire front in kilowatts per meter. The first thing is that we can see that there is here a regime close to x equal to 0, in which the intensity is low. This is because the fire was accelerating, was taking this, what I call thermal momentum, was getting to a point in which, reached a steady state kind of movement, right? And that's why it was quite slow. The second thing, and that's pretty interesting, is that this method allowed also to capture the change of regime from a linear fire to a parabolic fire. So you can see these two things here, this kind of blue. Can you see my mouse? Yes, right? So this blue, can you see my mouse, Ciruyo?
Not now.
Okay, so I'm gonna
no,
move
we
here.
can't.
So I'm gonna move here. You can see now.
Yeah, no,
Now we see.
No.
Okay,
Now we see.
okay. Yeah, that's what I was asking before. So what you see, so basically this area that you see here is, the fire is moving this direction, all right? So this area is where the fire starts to take this momentum, right? So that's why the intensity is low. And then what you see here is basically what resulted from the change from a linear fire to a parabolic fire. This is basically from the flanks of the fire, which always have smaller intensity than the fire front. Now, something also that I would like to draw your attention to is that the average value, if you take all of the data points, like more than 200,000 data points, and you do the average value, you might get something like 14.3 kilowatts per meter, which is what is consistent with other studies, and it's actually a high intensity fire, but it's actually not representative of the different values that we can find in here. It's actually, we found that the intensity varies a lot. Actually, there are some regions in which you will find intensities that goes from 2,000 to 10,000 kilowatts per meter square, others that goes from 10,000 to 40,000 kilowatts per meter square. There is almost an order of magnitude of difference. And that's something that I would like to highlight because, sometimes if you use intensity, only one average value of intensity to do calculations, for example, for estimating the amount of heat flux produced, radiant heat flux produced by a fire to quantify the risk of a house to ignite or something like this, then you need to account for this variability and try different values that account for this type of variability in intensity, knowing that this is a single fire and is under the same weather conditions, right? So that's something that I found interesting from this approach. Now, the second thing that we did, wow, time is passing super quick. The second thing that we did is to take this map and then try to estimate what is the flame height from it. Because if you look at the literature, there is a lot of research looking at how to relate the intensity of the fire to the height of the fire, right? We've done is that we took, during the experiment, we also included two poles, one pole in here and the other one here, and then two cameras looking at the poles from the outside. And then we were able to record the height of the fire from those two, which is what you see in this point, the blue one, and the other one here, right? So this is the x-axis, goes from 0, I mean, in this case, from 40 to 160. So it basically goes from in this area that you see in red, right? And then what you see in blue is the average value and the standard deviation of the height of the fire that was recorded. Then what we did is that we used these two results and we use a function looking like this: height of the fire equal to a constant times intensity, power, another constant. And we found the best values of those two constants in order to fit our model to the experimental results, right? And then what we've done is we use this one to extrapolate and have a map of flame height. So what you see here is an estimation of the flame height and a map of the flame height, right? Of course, we only have two validation points. We are working on getting more, to do this approach to other fires to see if the model works well. But I think that is interesting just to see, hypothetically speaking, how a map of the height of the fire will look like at this resolution, right? So the values that we see here goes from more or less close to 0 to 10, right, which is small flame heights in the initial part of the fire, but also with small flame heights at the flanks of the fire, right? The maximum values are close to 10 meters, which is something that we saw in the field, was more or less what I experienced when I was actually watching this experiment very close to the field. So it seems reasonable, right? And I think that this is an interesting opportunity, if we're able to validate this further, to see if we can actually do some kind of more advanced estimations of the exposure produced by the fire, right? And I think that there is a lot of potential with this approach. Now, just takeaways, 3 takeaways from this part. Intensity and flame height mapping is a promising new method to estimate wildfire behavior, also to estimate the impact. So let's say the heat flux produced by the fire and the severity of wildland fires. Intensity was found to vary a lot, more or less 1 order of magnitude, and this variability should be considered in risk assessment methods. And finally, this analysis, this future work, will be extended to other data points, other experiments that we've done, in order to increase the validation or confidence on the approach, and also to explore variability of intensity. All right. So I'm gonna now talk about the second one. I want to know how much time do I have in order to see if I just talk very quickly or I talk slowly. Can you just let me know, Ciruyu, how much?
I mean, the time is flexible, but technically speaking, 20 minutes.
Oh, beautiful, perfect. 20 minutes is perfect.
Yeah.
So that's very good. So, all right. So let us talk about the second one. So the first one, it wasn't talking about energy production from the intensity perspective, which is more like the classical approach used in wildland fire science. Now the second one is more like an attempt to introduce heat release rate into wildland fires. One of the challenges in wildland fires, in wildland fire science, is that we usually deal with big fires, right? Like fires that can go beyond 100, 200, 300 meters, which is impossible for us to put something under a calorimetry like we do in fire engineering and measure the heat release rate. So this is one of the main reasons why using heat release rate is difficult, because getting validation is very complicated, right? So this is just one attempt to actually get there, to start introducing the concept of heat release rate, and in this case, in a grass fire experiment. So this is another experiment we've done here in New Zealand. Again, this I think it was also done in the context of the project that was led by Zion in collaboration with our colleagues from other universities around the world and also internally. This one was a wheat stubble fire. So you can see the video here. So several things about this. With the first one is this particular experiment, we had 3 fires ignited simultaneously, one with an ignition line of 14 meters, the other one 37 meters more or less, and the other one 56 meters. So, 3 fires ignited simultaneously with different ignition lines. Sorry, 14, 37, and 56. Right? You have the conditions of the fire here. And also the fuel load was more or less like 0.47 kilograms per meter square, which is more or less like 10 times less than the other experiment that I showed you. So this is closer to a grass fire, wind-driven fire, very quick fires. Basically what we've done is we did some destructive sampling in the field. So, taking information about how much fuel was there, kilograms per meter square. And then what we've done also is to record the evolution of the fire over time using a UAV technology. In this case, with the camera basically attached to the fire. And the method that we developed basically start with this. We separate the fire, right? So for example, we take images from this fire. And then what we've done is that we applied a color thresholding approach that was developed previously in order to isolate the burning area of the fire for each one of the frames of the videos. And then what we do is that we use this approach to create a map of a residence time. Residence time means the duration of the combustion, the duration of the fire for a certain location, right? So that allows us to create this map of duration of the fire for a certain location based upon the time in which we see the fire happening, right? These are a rough estimation, but it actually works very well. Then what we've done is that we use this map, we take the fuel load, we use this map, residence time map, then we multiply that by the heat of combustion, right? And then we apply another algorithm in order to produce the video that you see here. This video, this is the core principle of the whole thing, but this video basically shows the production of energy, or let's say a time-resolved heat release rate over time. Sorry, time-resolved heat release rate, right? So it means that what you see here in colors is the production of energy from the fire in kilowatts per meter square, and it comes from this approach, right? So this is very, very interesting, because now we're able to access or to estimate, to look at the fire from another perspective, right? To estimate the total amount of energy produced by the fire, and not only by the fire front. We're also able to think in terms of variables that we can actually measure in the lab, right? So it allows us to get a good sense of how big the fire is, or you know, what is the potential of harm of the fire from something that we can directly relate to what we observe in the lab, right? So I'm going to give you some examples of this, and you will see what I'm talking about. One of the things we can do with this is to measure for each one of the fires the total amount of energy produced by them, right? So what you see here is heat release rate in megawatts for each one of the fire. So this is the high, I call it high, medium, and a small fire, right? It's very interesting, because if you look at this, for the one fire with for this fire, we have almost an exponential growth rate, which make us think of a typical alpha t-square thing. You know, it's like there is some type of exponential behavior that is going up. And you can see how quickly the fire actually grows in this stage. You know, the fire, we don't have more time, but I'm pretty sure that if you just keep going, the fire is just going to grow and grow and grow. This is also related to the fact that the fire is also expanding the area that is burning, right? However, if you look at this one is very interesting, because it seems that it's not really increasing in size, and it's not really increasing in energy production over time. So when you look at this small one, which is basically this one, I call this the zombie behavior, because it really doesn't evolve. It seems that is just a type of fire that is gonna just keep going and going without really kind of, you know, start growing, right? Which is interesting to quantify this, because maybe there is a limit in the way in which we can, maybe there is a regime actually associated to the way in which we ignite fires that will create fires that under the same wind conditions won't increase in size, right? Which is interesting. You can see the other one. I'm very interested in this one, because it's a clear, you know, it's what I would expect, if you want, from a wildfire. Is that wildfire, as we're talking about, a big portion of vegetation burning, I would expect that the tendency is actually to just keep growing and growing and growing over time, right? But this one illustrates the nature of the regimes that actually we can observe using this approach. And something even more interesting is that if we divide this total amount of energy produced by the fires by the burning area of each one of the fires, then we get something like this, something that seems to converge to a constant value close to 150 kilowatts per meter square. This is very interesting, because this is more or less the value that we find, you know, in labs. Also suggest that might be some kind of magic number, some type of number that maybe can be used to validate models or to calibrate some softwares of fire spread, or maybe to you know, to develop new ways to estimate the growth of the fire, right? It suggests that there is some type of physics that we don't understand yet that can be actually uncovered and unboxed, and allows to think the problem differently if you want, right? Now, the last thing that I want to show you about this one is very exciting, is this. We also try to go a little bit deeper and understand more about, this distribution of the fire, the way in which the heat release rate is released. So what we've done is that we took the fire, let's say this one, and then what we've done is that we quantify the heat release rate at different locations along the perimeter of the fire. So for example, this point is this one here. This is the angle. So the angle starts from 0 at the fire front and moves from 0 to 180, and then 360, and also from 0 to minus 90 and minus 90 and minus 180, right? So that's what you see here. So this point is the energy produced by the fire front, and this point basically is this one here. In blue, what you see is what we get from the experiment, and in black is one of the models that we developed. Is something that has been already proposed in the literature, but is something that has not been. I mean, it's the first time that actually we measure it in this with this let's say resolution. Now, if we look at this, we start working on the development of a model. It's actually very simple, but I think that is elegant to describe the distribution of the heat release rate in function of the geometrical characteristics of the fire front, which can also be attached or linked to the time, right? So basically what we have here is a model that allows us to understand what will be the distribution of the fire front. For example, what will be the heat release rate at the fire front location or at the sides, right? And based upon the geometrical characteristics of it, right? So I think that this is an exciting opportunity also to maybe improve our models. This needs a little bit more of analysis and validation, but I just wanted to share with you to see, where we are at in this analysis. 3 takeaways from this one. Estimating and mapping heat release rate is a promising new method to characterize grass fires, not only grass fires, also other type of fires. 2 regimes we identified, one in which we have an exponential growth of the fire, another one in which is basically non-growing fire or zombie regime. And a new model is under development in order to estimate the distribution of the heat release rate along the perimeter of the fire. And finally, future works, we will keep working, analyzing other grass fire videos and getting, a little bit more details about those measurements and models. And then we're also going to apply this model to a shrubland fires, so bigger fires, to see how they work. All right, I would like to acknowledge PhD student Kate, Jehan, and Fergal, funders of this research, MBIE Fire Research Group and the University of Canterbury. Also local collaborations, so Marwan Katurki and his team, Sion, Firemen in New Zealand, also Tom Logan, and finally international collaborations, US Forest Service, University of Melbourne, Covey, and San Jose University, and also the Sion field crew that helped to get all this data and helped a lot to actually get all this experiment done. Also Firemen in New Zealand, of course. And I would like to thank you to spend this time with me. Hopefully was about 1 hour, was good. And any question, please let me know. Thank you.
Thanks, Dr. Andres, for such a great presentation. Any question from the audience online? And we actually got one question during the presentation. It's related to the shrub fire, and Mazia asked asking what was the median intensity of the shrub fire versus average.
That's a good question. So the mean one.
The median.
I can send you that via email. I think I don't have the data right now. But if you send me an email, I can give you this information, because I think that I would just calculate the average value. And as we saw that there was so much variability in the values, an order of magnitude, then I think we didn't pursue really. But yeah, if you send me an email, I can maybe look at my data and let you know. Sorry for that.
And we get another question from Wenxuan. It's like, could you remind us the relevant publication about the glass fire heat release rate, like the mapping and the estimate, and he just would like to rate it.
Oh, but okay, it's under publication. So once I get it, I will think of you and I'm gonna send it to you. So I think that if you remind me, if you make just a quick email, I'll let you know exactly when it goes out. So it's a work in progress, actually. The first time that I show it. I also have this one, Anwar.
Yeah.
How is the power intensity of the moon? Oh, that's a very good question. So usually what I think in 95% of the cases, what people do is they take a average value of a rate of a spread. So for example, you take a chronometer, you take a timer, and then you measure how long it takes the fire to move from one point to the other one. So let's say 100 meters in, I don't know, it's 2 minutes. And then you calculate rate of a spread. And then what you do is that you take one single value of a fuel load, and then then you go for it, and then you just do one simple calculation. And it's often, what you want to get is some sense of this power of the fire, and not a in-depth physical understanding of what is happening, right? And it's more like, the way I see it is more like, usually it's like more from an operational perspective. It's like, okay, I just want to understand more or less how big it is, right? But this more or less sometimes is a big more or less, right? So often you go for a average value of rate of a spread, a single value, an average value of fuel load, sometimes from measurements, sometimes from tables, and then an average value also of heat of combustion. There are some values in the literature that are kind of always used, but in our case we use the lab, but you can use other type of values. So it's just basically a single value using average values from other sources. Does it make sense? Thank you. Oh, okay, excellent. Marcia, okay, I have it here. So I'm gonna copy your email. Thank you. I have another one here. Sorry if I missed this. Is it your intention to be able to use this work and translate it into live, real-time monitoring, such as wildfire? Okay, to provide advice for relevant organizations. I think that's an excellent question. We are not working right now to get this method applied in real kind of live estimation of intensity, but can be perfectly done, right? At this point, our intention is just to go more into developing the methods, understanding the limitations of the method, understanding what we can learn from them more from a research perspective. But I know that there are some of my colleagues at I think at the University of Maryland, for example, Fernando and his team is working on more on the application of it. It's like what kind of metrics you can get quickly in order to inform decision makers during the process of suppressing the fire, for example, or evacuating people. And that can be perfectly used for this type of things, but it needs to be optimized.
Thanks. Actually, Josh asked the question I want to ask, like how it can be incorporated with firefighter or equip it like the residents. So we get another question. It's like as a fire front transition from a line fire to a parabolic shape, would you consider this as the build-up phase of the fire? And have you developed any method to determine the build-up phase from your experiments?
That's a very good question. That's a very, very good question. I'm gonna come back. I'm gonna come back to look at that. So, you know, when you look at the, if you look at intensity map again, we have, that's a very good question. We have, in my opinion, we have two build-up phases. The first one is here for the line ignition. So build-up means that it's developing the flame, right? It's developing the depth of the flame and getting into a quasi-steady state conditions. And then we have a second one, which is this one, right? In which we develop a parabolic shape. Now, however, I think that is in between is, yes, I can see a transition, a built-up phase, but now if we look at the other fire, if we look at the other thing that I show you, this one, and we look at the typical way in which the intensity is distributed, you always have higher heat release rate at the fire front, right? And then lower at the flanks. It means that naturally you will see a smaller production of energy coming from the flanks, right? So I will say that is both of them is a build-up phase, but it's also something naturally happens. And yes, we have developed methods to determine the build-up phase, mostly kinematics. It means we try to characterize the acceleration of the fire. So we've been working on trying to characterize, you know, the changes in heat release rate and see how they relate to the characteristics of the flame, more specifically the depth of the flame, you know, the size of the flame. So if I come back and show you this one, you will see what I mean. Basically means how deep is the fire. So if I come here, you know, it's trying to see how does the acceleration of the fire to reach this quasi-steady state rate of spread relates to the size of the flaming zone, right? Or the depth of the flaming zone. In this case would be, you know, maybe 30 meters back, right? So we've been doing some work on that. And I think that's a good way to actually explain some of the processes that we can see experimentally.
Thanks very much. We get another question from Edward. Like, what happens if we overlay the intensity map and the field load distribution map and the multi-state and the field arrangement?
That's a very, very good question. Actually, we've done it. This is published, so I might send you, but the publication. But basically, what happens is that if you overlap them, and then if you plot a scatter plot, so point plot of intensity versus fuel load or vice versa, you will see that there is a relationship between them, of course, because you know because one depends on the other, but is a stronger relationship than for the rate of spread. What I'm trying to say is that the fuel load is, what we see is that the fuel load seems to be the driver metrics that controls how much energy is produced, which seems logical, but you know, this is because the rate of spread under the conditions that we study is quasi-steady, doesn't change too much. It's kind of always close to 0.9 meters per second, right? Now, if we look at maybe some specific regions, maybe the build-up phase or the flanks, that relationship might change. But for the overall fire, there is definitely a clear indication that the fuel load is you know, between the fuel load and the rate of spread, the fuel load seems to be this variable that actually drives the intensity, right? And that's super interesting because what it suggests is that maybe by having a very good understanding of the fuel load, maybe by having a map of fuel load for, I don't know, a certain region from potentially from satellites or from LiDAR data, maybe we can use this information already to calculate the potential intensity that can take place there, and not only calculate but also map it, right? So I think that's where we're trying to go with this one too, is maybe see if there is a way for us to maybe do some assumptions in terms of rate of spread. Rate of spread is very well studied. There is a lot of literature on how to come up with good estimations of it, and maybe focus on getting very good quality data from the fuel load and then use it to calculate intensity, knowing that that's the kind of the driver of intensity, right? But that requires a little bit more of work, and I think that's something we want to do in the future.
Thanks. We get one more question from Nadia. Like, as this burning experiment, do you think those findings will be translated in wildfire settings?
These are prescribed burns. Oh, that's a good one. Well, that's a very good one. I will say yes. And I guess maybe they cannot be directly translated, but we can definitely learn things that can be translated to wildfire, right? Like to real scenarios. So, you know, I don't know how close we are actually to take a video from a drone for a real wildfire and apply this method. You know, we haven't even thought about this yet. We're at the phase in which we're just developing the theory and the models for prescribed fires and only grass fire scenarios, right? We're still far away to apply this to not far away. I think close to apply for shrubland fires, but I think there is a lot of things that we need first to kind of understand and maybe kind of tweak a little bit, you know, in order to make this a little bit more insightful before we think of applying this to the wider scale, right? But it's definitely something that can be used. Something that I believe that can be used definitely is maybe not a wildfire setting, but mostly like a prescribed fire. You know, so for example, the zombie behavior that we found, these conditions for the fire to don't grow potentially can inform people doing prescribed fires to don't go beyond a certain value if you want to keep it safe, right? That's something that we can definitely learn from looking at some experiments, doing some analysis, and say, look, you want to keep your fire at a 20 megawatts. That's it. Don't go beyond 20 megawatts. How you don't go beyond 20 megawatts? Don't ignite more than this, or don't do it after. Don't do this after or during those wind conditions, or don't go beyond this fuel load, right? So I believe that at least allows us to get clear metrics and numbers, you know, that can maybe inform the prescribed burns, which are actually one of, you know, is a big cause of fires around the world. That's maybe something that I will suggest in this case.
Well, we'll get one more question from Anwar. Say like he would like very interested to see the effects of the wind on all those values, and if we could, grow two identical forests and burn them under different weather conditions.
Oh no, it will be it's so logistically difficult to do those experiments. It's crazy. In the future, hopefully in the next year, so Zion, the Crown Forest Institute here in New Zealand, might be organizing a pine prescribed burns. So that's an excellent opportunity for us to actually upscale this, right? Start to think and apply those methods for a crown fire potentially, which is the biggest type of fires that we can think of, right? So it means that this is a great opportunity for us to improve those methods.
Thanks. And Anwar said, like he noticed you mentioned the satellite imaging as well. Does the methodology you present over here can be extended to the satellite image as well, and what the data loss in the satellite image from the UAV?
And that's also a very good thank you for those questions, Anwar. This is very good. Okay, so I don't know if we can. To be honest, it's still very early to say if we can apply those methods or not for satellites. And the reason is that we're looking at the phenomena at the sub-meter scale, and satellites are going to give you the minimum resolution might be something, the minimum you can find might be maybe 100 meters. So, in this case, what we are developing will be maybe 1 pixel of an image produced by a satellite, right? So there is an extra work to be done is to see what will be the influence of the, of the scale on all this approach, So that's another question that we haven't done, kind of started solving yet. However, what I can do is that something that we can really extend to satellite images, and that's kind of my dream, is maybe not yet this type of result, not yet heat release rate from a prescribed burn of 100 meters by 100 meters, but maybe results from laboratory, right? So what we are doing now, there is one PhD student. She's developed a method to quantify flammability, heat release rate, to quantify heat release rate from, in this case, gores in our lab. And what she's doing is looking at different conditions for that, and being very careful on the fuel load, the height of the gores, and the condition of the gores, which is basically what you can get from satellites and drones. So what we're trying to do is basically replicate a piece of vegetation and try to quantify very well all those metrics that we can measure from satellites, and then do experiments in our lab in order to get metrics like peak of heat release rate, duration of the fire, like metrics that has units like heat flux, right? And then what we're doing is, before each experiment, and this is our colleagues from the Australian National Universities, Marta Yebras and Nicholas Yoon's team. So what they're doing is, before the experiment, they take images of the vegetation. So images, I mean, they take what we call a hyperspectral images, which is basically taking images at different spectral bands. So you take images at the blue band, at the yellow band, at the green band, and then we go for the infrared, and then we get like more or less 200 images per plant. And then what we can do is to see if there are some of those spectral signatures from the plant that can be related to some of the metrics that we measure in the lab, right? And then what is interesting from that is that we can take this equipment and then put in the space, and then look at gores, and then try to map flammability from gores, potential of harm from gores. Maybe not spread of the fire, but at least heat release rate or some type of metric that allows us to know, all right, this type of vegetation with these conditions, they might burn more or less this way, right? And maybe that's the first step before we think of implementing these type of measurements in satellites. Make sense?
Andrea, this was absolutely fascinating. Thank you so much for your presentation today. I enjoyed myself tremendously.
Thank you very much, and thank you for the questions, man.
Okay, we got lots of questions from the audience. And any last minute questions? Right. So it seems like it's about time to end this seminars. Thanks again. Appreciate your time, Dr. Andres. Such great presentation and a really good answer for all kinds of questions. I was surprised we received so many questions from the audience, and all of them is good, really good questions. Yeah, right. I think thanks everyone to attending. Thanks, and Dr. Andres. Have a good weekend.
Thank you very much for all the questions, and
I guess you had 3 hours in advance.
Yeah, I'm going home now.
To start your weekend. Yeah.
All right. Thank you very much.
See you.
Bye.